we're going to talk about a new topic, which is chemical equilibrium. Okay, so for your information, I will prepare about 3 different videos just only for this topic, because every video will talk about different things. There are so many things that we're going to discuss on chemical equilibrium, which is for the first video, this first video. Okay, so I'm going to let you know what is a reversible reaction. Okay, so we have irreversible and reversible reaction. Okay, and then we're going to discover about dynamic equilibrium, so its characteristics of dynamic equilibrium, and we're also going to learn on how to write down equilibrium constant expression in the terms of concentrations and partial pressure, and how can we relate these two by using this kind of formula, which is Kp equals to Kc RT delta N. Okay, so first, before we go in details about reversible reaction, let's understand first about irreversible reaction. So most of the things in this world are irreversible reaction. Irreversible, what does it mean? Irreversible means the reaction can only proceed in a single direction, and that single direction only referring to forward reaction. Okay, so for example, this one, I have all the ingredients I need to bake a vanilla cake. Wow, that looks so yum. Okay, we can just purchase it from secret recipe, but why not sometimes we want to bake our own cake? Let's say we want to make a surprise for our special person in our life. Okay, so this just a simple vanilla cake with cream cheese frosting between the cakes and on the top. Okay, to make a vanilla cake, I will need all the ingredients. Okay, from these ingredients, after mixing all the ingredients using a mixer, okay, after mixing all the ingredients together, and then spread out the batter in the baking tray and put it in the oven and bake for 20 minutes. Okay, and then we get our vanilla cake. Okay, cooling it down, and then we can mix our cream cheese to form a cream cheese frosting, and then we can spread out into layers of cake and on the top. Okay, at the end of the process, we'll get a vanilla cake. Now my question is, can I convert my vanilla cake back to all the ingredients I have been used before? Milk, eggs, butter, flour, okay, cinnamon powder, cream cheese, vanilla essence. Can I get it back? Definitely no. So that means a cake cannot be converted to its original ingredients. So that's why baking a cake is an example of irreversible reaction. And for an irreversible reaction, we will use a single double-headed arrow. Okay, so let's look for another example. So growing up is a process. So does a growing up is an reversible reaction or irreversible reaction? Can I, like say now I'm about 30 years old. So can I return to my old age around 10 years old? Or maybe I miss out my childhood memories. So can I return to when I'm just 8 months old? Definitely cannot, because growing up is a continuous process until the day you die. So growing up is an example of irreversible reactions that we face every day in our life. Okay, so let's look for reversible reaction. So if irreversible reaction can only proceed in one direction, and that direction is just a forward reaction, but for reversible reaction, we can proceed our chemical reaction in both directions, which involve forward and reverse direction. Okay, so what is forward and what is reverse? Okay, so let's say I have a reactants and forming a product. Okay, so from reactants to product, this one is my forward reaction. Okay, if I want to convert back my products to reactants, so this one is my reverse reaction. Okay, so for reversible reaction, we're going to use an arrow, a special arrow. Which one? Forward, we just use a double, sorry, it's not a double, but single-headed arrow. facing forward, and another single headed arrow which is to face reverse direction. So you're going to use a lot of this reversible arrow for the entire chapter 6 and later on in chapter 7. Okay, so this one is a simple example where we can have a reversible reaction in our kitchen. Okay, so I have liquid water, and then I decided to make ice for my water. Okay, so I allow my water to undergo a cooling process in the fridge. So the water become freezing and change to ice. Okay, so the forward reaction is freezing process. So this is a forward reaction. And let's say after I've taken out the ice and I forgot to use it and left it in the room temperature, so my ice will not continue to be an ice, but instead after leaving it sometimes in the room temperature, it will convert back into liquid ice, undergo a process we name it as melting process. So ice changing into water. Okay, so this one is a reverse reaction. Okay, so water to ice to water is a reversible process. Okay, so another example. Okay, I go to the supermarket and I suddenly crave for Cadbury chocolate, and my favorite is hazelnut Cadbury chocolate. So let's say you want to give me a surprise gift, give me a Cadbury chocolate with hazelnut or almond. Okay, so I bought the chocolate in the supermarket and then I leave it in my car's boot, and I completely forgot about my chocolate. I just returned home, spent a lot of times with my family watching TVs, watching K-dramas and so on. And suddenly late in the afternoon, late in the evening at around 6 p.m, I suddenly realized that I left out my chocolate in the car's boot. Okay, when I returned to my car and I found out my chocolate's already melt. Okay, melt chocolate. Okay, and I cannot eat that directly. So what I'm going to do with my melted chocolate, I will keep it in the fridge, allow the chocolate to freeze, okay, until it forms a chocolate bar again. Okay, so this definitely not a chocolate bar, just imagine it's a chocolate bar. Alright, so and then I will get my chocolate bar and ready to eat again after a few hours of keeping my melted chocolate in the fridge. Okay, and then from the chocolate bar, suddenly I saw fresh strawberries in the fridge, and I said, why not if I try to dip this strawberry in a melted chocolate for my snacking time. Okay, so I get my frozen chocolate or my chocolate bar and I melt it over the hot pot until it turns into melt chocolate. So melting process, reverse reaction. So this one is a forward reaction. So from melt chocolate into a chocolate bar or chocolate cubes, okay, we can change it from one to another, and that's why handling with chocolate is a reversible reaction, which you can go both forward and reverse direction. Okay, so enough with the food. Now let's get back to a more serious issues. Okay, so here I write down what is forward and reverse just for you in case you miss out what I wrote in the previous slide. Okay, so forward reaction is from left to right. Okay, so from reactants to product, so this is forward, and from product to reverse, this is reverse reaction, from product to reactants. And a reversible arrow is being used to show the chemical reaction is a reversible reaction. So this is the reversible arrow. Okay, I don't want to see you to use this kind of arrow to indicate reversible reaction. This one is completely wrong. Okay, so we use a single headed arrow facing forward direction and another single headed arrow facing reverse direction to indicate reversible reaction. Okay, so Haber process is an industrial process to produce ammonia. So this one is a common example of chemical equilibrium, chemical reactions that chemical reaction which is a reversible reaction. So nitrogen gas reacting with hydrogen gas to produce ammonia. Okay. So in again, we use this reversible arrow. Okay. So this is a plot of concentration versus time. Okay. So this kind of plot is quite famous to shows reversible reaction. Okay. So these reactions is to show the process of A gases changing into B and the reaction is reversible. Okay, and the reaction starts with A. Okay, so that's why you see A has initial concentration where B it starts from 0. Okay, so the reaction proceeds in the forward direction where my initial concentration of A started to decrease after certain period of time because we start to produce B. So concentration B increase, okay, increase slowly from 0. Okay, after certain period of time, okay, this straight line here, T1, okay, after T1 I can see the both concentration of my B and A does not change. It remains constant. Okay, so concentration of B does not increase and concentration of A does not continue to drop. So after T1, both of these reactants and product remain constant in the terms of concentration. And why does it happen in that way? It means after T1, the system already established a dynamic equilibrium. Or the system already established an equilibrium. Okay, so before T1, Q reaction quotient is not equal to K equilibrium constant. Okay, but after T1, Q now equals to K and the system's already established a dynamic equilibrium. So what is a dynamic equilibrium? So for a system to establish a dynamic equilibrium, it must have these three criteria to obey. Okay, so the first one, both concentration on reactants and products remains constant over time. Secondly, the rate of forward and reverse reaction is equal. And thirdly, reaction quotient is equal to the equilibrium constant. Okay, so this is an example of the reaction where my N2O4 gases change into NO2 and the reaction is irreversible. Okay, so I have N2O4 initially in the vessel, and as the reaction proceeds, NO2 gases start to produce. Okay, so N2O4 has initial concentration, N2O4 initial, and while my NO2 concentration starts from 0. Okay, so as the reaction proceeds, N2O4 concentration starts to drop because it's being used up to produce NO2. Okay, so concentration of NO2 slowly to build up from 0. After a certain period of time, which is T1, okay, I can see that both concentration of NO2 and N2O4 remains unchanged. Okay, so after T1, concentration of NO2 and N2O4 remains unchanged. Or in a simpler word, we can say remain constant. Okay, why does it remain constant? Because a dynamic equilibrium has been established. Okay, has been established. Okay, how can I prove that? Okay, so after a certain period of time, no more change in my concentration first. Secondly, my reaction quotient is already equivalent to K. Okay, Q equals to K. So first, N2O4 concentration and NO2 concentration constant. Okay, secondly, Q equals to K, and thirdly, the rate of forward equals to rate of reverse. So how does a rate plot of rate versus time looks like? Okay, so let's draw one. Okay, so as in my y-axis I have rate. Okay, you're going to learn in more details what is rate in kinetics chapter kinetics in your semester 2. Okay, and my x-axis is time. Okay, so forward reaction. Okay, from up to down. Okay, so this is forward reaction because we start to slowly use up. Okay, and then we start with reverse reaction. Okay, so reverse. Okay, so as these two forward and reverse reaction meet at one line and produce one plateau line, so this one we name it as dynamic equilibrium has been established. Okay, so initially Q is not equivalent to K, but after T1 Q equals to K, and I can see rate of my forward equals to rate of my reverse. Okay, so you have to remember that three criteria, which is the first one. After reaching the dynamic equilibrium, first, concentration of all reactants and products remains constant over time. Secondly, okay, reaction quotient is now equals to equilibrium constant K. Thirdly, rate of forward is equal to rate of reverse reaction. Okay, so what is reaction quotient and what is equilibrium constant? We're going to learn how to write down the expression for both of these somehow at the end of this video and in my next video. Okay, so let's now plot a curve of concentration against time for reversible reaction. Okay, so we can have either we start with my N2O4 in this example, or we can also have when we start with NO2. Okay, so if let's say we start with N2O4 gases, okay, so concentration on my y-axis, okay, so concentration has unit of molar, okay, and then time. Okay, so if I start with N2O4, so my concentration of N2O4 started to decrease. Okay, and then my NO2 concentration starts to build up, and NO2. So these are T1, which the concentration of both N2O4 and NO2 starts to remain constant. So this one Q equals to K, and before that Q is not equals to K. Okay, so how does it look like when I start with NO2? Okay, so NO2, again concentration on y-axis and time on my x-axis. Okay, so now I start with NO2. So initial concentration is my NO2, and N2O4 starts to build up. So these are my N2O4 gases. Okay, it just looks the same, but sometimes you can see the plot to be like this. Okay, so N2O4 and this one NO2. So T and this one is concentration. Okay, it's actually, it looks it's the same kind of plot. Is the difference now is in the terms of scale. Okay, so if the scale is very big, and then these two lines will not intersect with each other, whereas if the scale is too small, and then we can see and both of the curve for NO2 and 2O4 start to intersect at one point. Okay, as whichever this plot is, it just is a similar kind of graph. Okay, and still can show you where dynamic equilibrium has been established. So this one T1, okay, so Q equals to K at this area, and then Q is not equals to K at this area. Okay? Alright. So now let's learn on how to write down expression for equilibrium constant in terms of concentrations and partial pressure. Okay, so one thing that you need to remember, okay, whenever you're going to write down the expression for your equilibrium constant, pardon me for my wrong word just now, okay, so you need to remember any pure liquid and pure solid that presents in the chemical equation need to be removed or not to be removed from the equation, but we're not going to include the solid and liquid in the Kc or Kp expression. Okay, so equilibrium constant is Kc for concentration and Kp for my partial pressure. Okay, so we're going to discard any pure liquid or pure solid from the expression because we see that both of these concentration remain constant, so not going to change, so therefore we're going to omit that. Okay, secondly, we're going to state that Kc and Kp has no unit. Okay, they actually have unit, but you need to derive it. But for our syllabus here in matrix, we can just say we don't want you to derive the unit because it requires a long process. So we just simply state that it has no unit. So in the exam, strictly no unit for your Kc or Kp expression. Okay, so this is an example 1. Okay, so in my first example, okay, all the reactants and products are just gases. Okay, so write down my Kc. Okay, I'm going to write down my Kc first. Okay, I'm going to use square bracket for my Kc. Okay, so in the top, I'm going to write down for my product first, H2O. Okay, square bracket. Okay, bracket represent concentration. Okay, the square bracket represent concentration. And since my water vapor has stoichiometric coefficient of 2, so I'm going to put here as the power, okay, 2. Okay, then O2 concentration, and it has 1 stoichiometric coefficient, so I just ignore, don't have to write 1, over, okay, H2O2 gases, hydrogen peroxide, and it has 2 as the stoichiometric coefficient, so 2. So this is my Kc expression for this chemical equilibrium. Okay, if I want to write down the Kp, so P stand for partial pressure, H2O. Okay, so before that, in the Kc, I use square bracket, but for my Kp, I will use a round bracket. Okay, again, stoichiometric coefficient appear as power 2, okay, time with partial pressure of my oxygen over partial pressure of H2O2 and square. Okay, this P is italic and it must be a capital letter. And for my gases, okay, it looks like a subscript, very small. Okay, so this is my Kp expression. Okay, let's try with a different example. Now I have solid in both reactants and products. So write down the Kc first. Okay, C. Okay, so write down first PbO square SO2 square. So where does this square come from? Comes from the stoichiometric coefficient. Okay, so concentration Pbs square, concentration of oxygen, and the stoichiometry is 3. Okay, so remember the first rule, all pure solid will not appear in the Kc or Kp expression. Okay, so look at this Kc expression. Okay, PbO, so cancel out this one, and PbS cancel out this one. So we're going to write down the final Kc expression, which is SO2 square and O2 to the power of 3. Okay, so for my Kp, I can just simply change the concentration into partial pressure, SO2 round bracket square, and then partial pressure of oxygen, round bracket to the power of 3. Okay, so let's look for another example. Now instead of solid, I have liquid. Okay, so pure liquid is the same like pure solid, okay, will be discarded, okay, from K expression. Okay, so let's write down my Kc. Okay, so I have H2S2O7 concentration over H2SO4 concentration, and then SO3. Okay, before you start writing down Kc or Kp expression, you need to double check either the chemical equilibrium given is already balanced or not. If it's not yet balanced, you have to balance it first before you proceed with the equilibrium expression, or else your entire calculation or entire steps later on will be completely wrong. Okay, so put it in your mind, you need to make sure all the chemical reaction equation must be balanced. Either it is in equilibrium or not, it must be balanced. Okay, so pure liquid must be discarded. Okay, so pure liquid H2S2O7, mark on it, and H2SO4. Okay, so this one, since we can discard H2SO7, so we're going to replace by number 1. So 1 over SO3. Okay, so this is my Kc expression, whereas my Kp is simply 1 over partial pressure SO3. Okay, so let's give another example. So now I have solid. Again, solid needs to be removed from the Kc and Kp expression. So Kc is just simply concentration of CO2. So, okay, so remove. And Kp equals to partial pressure CO2. Isn't that simple to write down the equilibrium expression for both in the terms of concentration and partial pressure? Okay, key point, you just need to remember, always discard pure liquid and pure solid from the expression. Okay, so this example 5, okay, the final one, actually is just the same like your example 3, so just rewrite the answers. Okay, okay, so now how are we going to relate your Kc expression in the terms of Kp to solve equilibrium problems? Okay, so it involves a long derivation on how your Kp can be written in the terms of Kc. Okay, so I want you to check out your lecture notes for more detailed explanation. I'm not going to derive this expression. We are not going to derive this expression in this lesson video, or else our lesson video will be very long. So in this one I will just show you how can we apply this expression, okay, to solve any equilibrium problems. Okay, so in this one, so Kp is your equilibrium constant, okay, in the terms of partial pressure. Whereas your Kc is equilibrium constant, okay, in the terms of concentration. Okay, so R is your ideal gas constant, or is the gas constant. So the value of R is 0.0821 per mole per Kelvin, liter and atm. Okay, so T is actually temperature in Kelvin. Okay, and delta N is the difference in mole of gas. Okay, so N product minus N reactants. So N represent number of moles, and number of moles here is for the gases component only. Okay, so there's one. I have my nitrogen reacting with my hydrogen and ammonia. So this one is a Haber process. So Kp equals to Kc RT delta N. So first we need to find out what is my delta N. So delta N, I said that is the number of mole of gases component in the product minus number of moles of my reactants. Okay, so gases component only. Okay, so in my reactants I have 2 moles. Okay, so 2 minus in the reactants 1 mole from nitrogen. Okay, 1 mole plus 3 moles from hydrogen. So in total 4 mole. So 2 minus 4 mole. So my delta N is equals to -2. Okay, so in the question, it already gives you the Kc value for the reaction at 300 degrees Celsius, which is to be 9.60. Okay, so to use this as a K equation, okay, so you need to make sure the temperature is in Kelvin. So T 300 plus 273.15, which is equals to 573.15 Kelvin. Okay, so you convert first the temperature into Kelvin. Okay, then we're going to substitute into the formula. So Kp equals to Kc, which is my Kc is 9.60. R is 0.0821 per mole per Kelvin liter ATM. Then with temperature 573.15 Kelvin, and my delta N is -2. Okay, so press your calculator and convert your final answer into scientific form, which you will get your Kp to be 4.33 times 10 to the power of -3. Again, no units. Okay? Alright, so let's look for another example. Okay, so here N2 reacting with oxygen to produce NO2. So check first either the chemical equation is already balanced or not. So it's already balanced. So you have to calculate Kc and Kp at 350 Kelvin. So T is 350 Kelvin. Okay, they give you the initial mole. Okay, so 2.50 mole for nitrogen. For oxygen is 3.50 mole. Okay, for NO2 is 0.06 mole. Volume is 2 liter. Okay, so to use, to calculate the Kc, okay, so Kc, first write down what is the Kc. So your Kc is concentration of NO2 square over N2 and O2 square. Okay, so you need to first calculate the concentration of all the gases components at equilibrium. Okay, so how to calculate concentration from moles? So concentration is simply number of mole over volume. Mole, and the volume is in liters, so mole per liter. Okay, so let's calculate for N2. Okay, so it's 2.50 mole divided by 2 liters. You will get the concentration to be 1.25 molar. Okay, so for my oxygen, it's 3.50 mole divided by 2 liters. So you will get it as 1.75 molar. Okay, and for my NO2, okay, it's 0.06 mole divided by 2 liters. So you will get 0.03 molar. So you're going to substitute all this concentration into the Kc expression. Okay, so NO2 0.03 molar, okay, to the power of 2. My N2 is 1.25 molar, okay, and then my oxygen is 1.75 molar square. So if you press your calculator, you will get your Kc to be 2.35 times 10 to the power of negative 4. Okay, so we are done with the Kc, and now let's try to calculate Kp. So Kp can be calculated using Kp equals to Kc RT delta N. Okay, so first calculate the delta N for this equation. So I have 2 mole of gases in the products. Okay, minus with 1 mole from nitrogen gas plus 2 mole from oxygen gas in my reactants. So at final, my delta N is negative 1. Okay, so going to substitute Kp. Okay, so my Kc is what we already calculated before, 2.35 times 10 minus 4. Okay, time with my R is a constant, which R value is equivalent to 0.0821 per mole per Kelvin, liter and atm. Okay, time with my temperature, which is 350 Kelvin to the power of negative 1. Okay, so if you press your calculator, you will get your Kp to be 8.178 times 10 to the power of negative 6. Again, you don't have to state what is the unit for your Kp, because in our current syllabus, we can just simply state that both Kc and Kp has no unit. Alright, okay, so I hope you already understand what is a reversible reaction. Okay, so you already know how to discriminate between irreversible reaction and reversible reaction, and how to write down a reversible reaction in a form of chemical equation. Secondly, you already learned about dynamic equilibrium. So what are the criteria that you need to have before you state that the reaction already established a dynamic equilibrium. Thirdly, you already learned on how to sketch a curve, a plot of concentration versus time. Okay. Fourth, you already learned on how to write down both Kc and Kp expression, and how we're going to calculate Kc, like a simple calculation involving Kc, and how can we relate how can we derive Kp in the terms of Kc, and how to use that in the problem. Okay, so that's all for today's lesson video. See you guys in my next video with a more complicated question. Thank you for watching.